Hello everyone. Alright, Dr. Hashim is here with you, the lab coordinator. So in this video, I will show you how to use the NMR databank. Right? What that allows you is basically to predict the 1D proton NMR spectra, predict a 1D carbon-13 NMR spectra, predict some 2D spectra, but we won't be taking a look at those. So we'll really focus on proton NMR. So the link is directly through the module, but you could also type NMRdb.org and you'd get straight into this page. Well, we're really looking to predict a proton NMR. So if you take your mouse and click on that, right, you'll get to this page and it predicts the course using the structure that you're going to draw of the molecule, right? It will not predict protons that can exchange with a solvent, and those are really OHs and NHs, and this is the OH of the carboxylic acid group. So they're not predicted. Those protons won't show, right? If you have a molecule that's shown, just click delete. You really shouldn't typically see anything. Okay, so I'm going to go back to NMR predict. It should be clear. Okay, so you have some tools that allow you to draw. If you wanted to draw a benzene ring, if you wanted to draw a molecule, if you wanted to erase something, you can click erase. This is cyclohexane. If you wanted to add a branching point, a methyl. Suppose I wanted to add an alcohol. Look at it, right. It will right away go in and add the hydrogen to satisfy the octet rule with no charge. If you wanted to make an ether within the molecule, if you no longer want it into a cyclic structure, you have an eraser right here. You could erase. All right. You could, specify the chirality of the molecule if you would like. So anyways, if you wanted to, erase everything within this page, just simply click delete. So I'm going to show you very quickly how to use it to predict the spectrum. But one more tool, if you wanted to draw a long hydrocarbon, you can click on that. It shows you the lines and they're connected. And with your mouse, you could simply drag your mouse and it'll draw, right? It works by dragging your mouse and not necessarily clicking one by one. If you want it to click one by one, so we could use that. So suppose I wanted to make this carbon into an oxygen. All I have to do is take my mouse, make sure I'm clicking on that atom, take my mouse and put it right over that carbon, the position, and it will right away take it. Suppose I wanted to add a bromine on this carbon, I can add a bromine onto that carbon. Suppose I wanted to add another methyl, and if I'm satisfied with the structure and this is what I'm looking at and would like to simulate the spectrum, I can click on that and it'll show me another chemical structure. It's basically the same one, but it's showing you all the different protons at the different positions. So this carbon, it's a methyl, right? It has 3 protons. This methyl has 3 protons. So if you take a moment and take a look at it, what you want to do is basically, once you draw the molecule, ask yourself how many proton NMR, how many peaks would you expect on its proton NMR spectrum? Would it be a singlet, a doublet, a triplet? Would any 2 protons have the same environment and thus overlap? So if you take a look at the methyl right here, the protons on this methyl and this methyl, they basically see the same exact environment. All right, they're both connected to a carbon that's connected to another carbon, so those 2 peaks will overlap, right? And then you take a look at the splitting. Are those hydrogens attached to, one bond away? Do you have a hydrogen attached? So let's take a look at it more so right here. So if you take your mouse, and we're really not clicking as long as it kind of goes right over the protons, it'll highlight in yellow, it'll highlight the protons on here, it'll highlight the data table that shows you the assignments, the delta or the chemical shifts. It'll show you the multiplicity. Is it a doublet, a triplet, a singlet? D indicates a doublet, S a singlet, T a triplet, or is it a septet? Anyways, so all you do is you kind of pass over it. And if you take a look at those 3 hydrogens, they'll have a chemical shift of 0.96. Those 3 hydrogens are within this, protons are within the same environment, so their peaks will overlap into one peak, right? So think about that as a single peak, and nearby is 1 proton. So if you do the n+1 rule, that would be those protons would count as the 1, and this is the n, so 1 plus 1 is 2. Well, what you could do is actually click on one of those and it'll zoom right into the peaks, and if you notice, the peak is a doublet. It'll have an intensity if it's integrated that corresponds to all 6 protons, but it's a doublet. Remember, the splitting has to do with nearby protons, right? So if it's split into a doublet, it tells us that nearby there is a single proton, right? Which peak would you expect to be a singlet? Right here, we have a singlet. Again, you click through the table and it'll show you right into this singlet, right? It'll have an intensity when it's integrated that corresponds to 3 protons, but nearby, 1 bond away, you do not have protons, right? So if you wanted to zoom out to see the full spectrum, double click to zoom out, right? So we could double click right here. Notice all our peaks are within this region. We could click and drag, and then we could zoom in our region. We could go with our mouse higher and lower to, take a look at the intensity of the peak, and you could again click and zoom to take a look at the peaks, right? Double click to go back out, again click and then drag, highlight, or you could simply click right here. A single click will take you to the different ones. Remember, the J coupling is you're really looking at that distance between the splitting patterns, right? That's the J coupling. Remember, protons across an alkene that are cis or trans, you can identify those based on their coupling constants as well, right? But really not looking into the details of that yet. What else could we take a look? The chemical shift, right? You have ones at 0.9 parts per million, you have ones at 2, ones at 4, one at 3. Could you have looked at the structure and decided the chemical shift? Would it be more shifted downfield or more shifted upfield? Sometimes the easiest way is to look for electronegative atoms, because protons that are near electronegative atoms will tend to be shifted more downfield or higher parts per million. And if you take a look at this proton, it's near a bromine and an oxygen. If you take a look at the peak assignments, it is the farthest downfield or higher parts per million, followed by those protons. All right, and then this hydrogen is still closer to the oxygen. All right, notice the splitting pattern in this particular hydrogen is a septet, right? And that's because this hydrogen would correspond to a single peak, but it's going to be split by nearby protons. Now, those 2 protons have the same environment, so you simply say n+1. So this counts as the 1 peak, however many protons it has, but in this case it only has 1, and n would be 6. So n+1 is 7. All right, well, I hope this was helpful. Remember, you could double click. Feel free to use this tool when you work on your assignments and discussions. It's a very helpful tool to use, whether in lab or in lecture for practice, right? Suppose I wanted to check the proton NMR and I've already drew the structure. I could simply go in and click predict carbon NMR, I believe, and it should show you the same molecule, right? You could do calculate spectrum. How many carbon NMR peaks would you expect to see? All right, here they are. Remember, they're singlet, they're not split, and the window when we take a look at carbon NMR is slightly different. And it follows the same way, where you can click, highlight, and it'll actually highlight the peak, right? We're looking at carbons in this case. I truly hope this was helpful, and we'll see you next time.